Hello, everyone. Oops. Hello, do you hear me now?
Yes.
Yes.
Okay, very nice. Okay, there's some issue with my audio. Okay, so let's start today. The idea was to have a hands-on session on classification. So remember that on Friday we were studying classification algorithms for machine learning, and so we were looking at some models. We were looking at decision trees, naive Bayes, and I think finally we commented on logistic regression. So those were like three models representative of three approaches for classification, which is discriminative functions in the sense of models that a priori do not aim at producing probabilities as an output. And this is an example of decision tree. And then we saw two probabilistic models. The first one was naive Bayes, which has a generative probabilistic model, and logistic regression, which is a discriminative probabilistic model. The difference between these two models were the fact that while in the generative approach you need to specify the likelihood of your input, then in probabilistic models this is just not necessary. So you model the probability for a given class given an input directly from the data, and this is the case of logistic regression. So this is a very, very short summary of the lecture on Friday. And so the idea that I wanted to do today is, given the importance of decision trees or the use of decision trees, at least in physics community, but not only, right? So there is I am aware of, I don't know, at least the in consulting sector, this is also very, very used, quite used. Sorry, and so let us try to implement decision tree in Python, and let's try to do it from scratch. So the idea here, that what I wanted to bring to you is, first of all, taking into account that we are scientists, and hopefully we are not only caring about results, but about how we get those results. I thought it was a good idea to implement at least at least once, to implement from scratch this algorithm. And later, if you want to use it in your practical application, you can use a library or something like that, which there is plenty of it in the internet. But I just profited in the fact that we are physicists and that we want to understand things from scratch, right? So let us try to implement a decision tree from scratch. I am sharing my screen here, and as I was saying in my email later on Friday, I am assuming here that everyone here has a working version of Jupyter notebook. I mean, this Python notebook, or at least you could go to Google Colab. So in this case, what I'm showing you here is a local notebook in my computer, but you can go to Google Colab and then you start a session and then you do the same. So I was you say here new notebook, and then you are good to go. So essentially everything that I am writing, you can also do it with me. So the idea is just to write together some code. So is there anyone here that does not have these requisites? Okay, good. Okay, so if this is the case, let us start. The first thing that we will do is to implement the decision tree, but typically what we do is to import the necessary libraries in the notebook or in the script or whatever. So let me just start by writing the typical libraries. So NumPy, you know what is NumPy. I hope you know this is just a library for algebraic manipulation, etc., and many other things. So I am importing NumPy. I am importing for plotting later matplotlib as PLT. I am importing, and let's use a data set. Let's use a data set which is already prebuilt from scalearn. Scalearn, if you don't know, it is a library from Python which contains a lot of machine learning algorithms and a lot of numerical examples, a lot of data sets like you can play with. So let us import a data set which is called make moons. Okay, at least these three libraries for a moment, and then let us see what is this data set. So I am importing this data from where I'm just saying, let me put some noise because this is of course generated from some generative distribution and some random state just for reproducibility, but this is not this is not mandatory. And this dataset contains inputs and outputs that I am separating here. Okay. So once I have done this, I'm executing this. Then I am just plotting it, just to see what is this dataset about. So this is a two-dimensional dataset. I'm plotting here dimension 1, dimension 2, and the color of the point is going to be equal to the label, to the output of the point, and finally showing this. Okay. So this is the data set we're studying. We are using for our algorithms, and so you see it is called make moons because you see that these clouds of points have more or less the shape of a moon. So there, in this case, for two classes, you have like two moons like this, no? Like one inside the other, more or less. So is everyone at this level? Is everyone with me now, or so you have some problems by loading this data set? Okay, so please just interrupt me if there is anything that you don't understand or anything that it is not working for you. So let's take this data set, and the idea is to, of course, to classify this data set. So to build a classifier on this data set, let us see how many points we have. So let me just put this shape. So we have 100 points, and then from these 100 points, we will, of course, use some parts. So what we are going to use here is this overfitting control procedure where you separate in training and in test, right? So first of all, what we are doing first of all is to build a decision tree. So let us build decision tree classifier from scratch, and then I will use a library from scikit-learn in order to compare our results. But I mean, as I was saying, I think it is a good idea to do this once in your life.
Brian, can I take a look upward just for a second?
Yes.
Yeah. Okay, thank
you. So if you remember from the lecture of Friday, the decision tree is a greedy algorithm where you segment your input space like this. You segment it in different with different splits, right? And then you need to evaluate the different splits in order to decide what is the best one. In order to decide what is the best one, there is this notion of impurity that we were studying, and one of the ways in which impurity is used, which is very popular one, is this so-called Gini index. So let us write the Gini index, and by writing it, we are actually reminding ourselves what is the definition of that. So let us define a function which is called Gini.
Sorry for interrupt. But
yeah.
Could you show the first of the head of the program? Yeah. One moment. I'm going to take a picture. Okay. Yeah. Thank you.
So let us define a Gini, which is just this criterion for choosing the best split. Split, I mean, just I'm splitting the input space in patches, right? So Gini will have arguments, and the arguments is just an array, which is just data if you want, and some classes. For example, class 0 and 1. There are many ways of programming this, but this is the way I have here. So let us follow this. So I start with Gini equal to 0, and then I do a loop over classes. So imagine I have a binary problem like here. Classes here are 0 and 1. So K will have 0 and 1. Okay. Then I do the following. Let me just write the following. So this is the impurity, if you want, P or this probability, which you remember was some notion of fraction of points, right? So if there is a fraction of points obeying some condition, is a fraction of points where my output, an array here is data, and so data consisted of let's say x1, x2, and y, no, which is the last column of my data if I visualize it in this two-dimensional. So data is just okay. Data in this case is written in this way, but I will let us transform data just to see better. Let us transform first the data. So what I will do here is going from this to some notion of some data set, which I will transform in the following way. So let me put data set equal to a horizontal stack of columns, right? Of input and output, and with some this output I will just reshape it because it is from a row vector to a column vector. Okay. So if data set is this, then let me just check what I am doing here. Okay, so this is what I wanted to get. So I have a data set which is having 3 columns. The first 2 are the input points, and the last column is the output point, is the output value. So class 0 class 1, right? So by doing this, the argument of Gini here is this data set in this format. So this only means that for all the points, take the last column. So I am taking the output column here, right? Okay, so then what I'm saying is, okay, imagine for class K, what I'm saying is that numpy where this is equal to K, right? And where this is equal to K means, for example, if K is 0, because I'm talking about class 0, then I'm saying all the points having, so what is the number of points having class 0, for example, okay? And so let us, in order to understand this, let us do this here. Let us do this below for you to understand what is happening with this line. Imagine that I have this array, of course, yeah, data set. So let me see. Data set, length of data set, what it is. I have 100. So now, what is it? Now, if I put numpy where data set is equal to 0, okay. So those are the points where the data set is having class 0 if you want. And if I just take 0, I mean, this is
one thing, one moment. Can you
Yeah.
show the definition of data set? I think I did the reshape.
Yeah. The reshape is only done to y because y is it's like a row vector, and I'm trying to put y has
Perfect. Yeah, I got it.
So you see what this line up here is trying to do is to have the number of points. This is by this length of the array, if you want, where the last column is equal to 0. So the number of points having output equal to 0. Okay. So let me just back here, and then I will just copy paste this. But now I'm putting K because I'm running a loop over K. And this I divide by the total length of my array, of course, because I'm talking about a fraction here. So this is my impurity, if you want. And then with this impurity, then you remember what Gini was. So of course, Gini is a sum over classes of pk times 1 minus pk. Okay. So this is my Gini, if you want. So and let us try to test this function. So if I now call okay, I need to return Gini. Sorry. Return Gini or Gini. Okay. So let us check this function, Gini of dataset, and classes are 0 and 1, because I have only two. I have only two classes. Then the Gini is 0.5. Why it is 0.5? Because essentially there is a 50% points from one class and from the other class. Okay. Is it clear what this Gini is doing? Okay.
Can you hear me?
Yes.
Shouldn't you change in your function of the impurity change dataset to R? Otherwise,
Yeah,
I'm not
I
sure
was
why
about
it
to say that.
works. But
It works because dataset is already defined.
oh,
so
it's already
the same.
initialized.
Yeah.
Yeah,
Yeah. Sorry.
it's
Sorry.
coincidence. Yeah. Okay.
Yeah. Sorry. Yeah. Is R here? Okay. So then, thanks for clarification. So then, once I have a definition of my Gini, so then I need a function to make the split. So I am calling here data dat. Sorry for calling it differently, but this is the data if you want. This is the index of the variable, I bar, and this is the value of a variable. So I am collecting here in left and right the data that goes to the left of the split and the data that goes to the right of the split. Then what I'm doing is running a loop over the data points. So I am running a loop of the rows, if you want. So something like that. And then I'm saying if that in J, which is the variable, right? I bar. So this is the point, the point, the specific point, and the specific variable. If this is less than value, then go to the left. So this point belongs to the left branch of this. Let me call this a node. Then I am appending to left this data point. Okay. Else, I am appending it to the right. So you understand what it's doing. So I am evaluating for a given split. So I'm given a split is a variable with the value here. I am splitting the data to the left or to the right of this value. Okay, so let us, as we did before, let us evaluate this. So if I evaluate this data set, and let us choose, for example, the first variable, 0, and some value here, which value, for example, 0.5, let's say. So I am I'm evaluating this split here. And as a result, I will have some points at the left and some points at the right, right? Okay, so I again forgot to do the return, but before doing the return, I'm just reshaping the return, the left. So left is going to be an array, because so far it's not an array, it's just a list. And then I need to convert it to an array. And this array, I am reshaping it in a given way. So I'm reshaping it to be just as many number of rows I need when I mean, I'm just saying that this is this value is 2 here because it is the number of variables. And then I'm doing the same for right. right, I am converting it to an array. And right. And then I'm finally returning left and right. Okay. So let us evaluate this. When I evaluate this, I am left and right is equal to this. So let me see what is left. So left is all the points that are to the left of that particular split, and then let me see, there are 51 of them, because I have chosen a cut value which is quite central. But if I would have chosen like 1, for example, then of course to the left there's going to be 71 points. So I am evaluating it here instead. So, and similarly to the right, you have 29 points going to the right of that split. Okay. So let us continue on that. Now that this function, what does is just to split the data set given a value of the variable in question. Okay. Then let us evaluate among all the splits. Let us create a function that tells me what is the best split. And best split will have, of course, as an argument, will have some data and some type. I will explain this right now. Well, probably. Yeah, so maybe I am not, well, I will do these types because it may be useful for you for the future. Types is if the input is continuous or discrete, because this is an algorithm that can be used whether you have a continuous input like this problem, or whether you have like a discrete input, like for example, if you have a problem where the input is in some poll, say, tell me from to a person from A, B, C, D, what is your choice about some problem, whatever. So this can be a categorical variable, what I'm saying. And what I'm saying is that decision tree written in this way can also handle categorical variables. So let us put this for a moment like this, and then I explain how to deal with both types. So first of all, let me just define here for convenience the number of the dimension of X, if you want. Okay, and then I will like fill this array, which for now is empty. So this array will store the results of my splits, of all the splits. Remember that in decision trees, what I was telling you the other day is that you evaluate all the possible splits of all the possible dimensions, and across all of them, you choose the best one. Okay, and this array split res will have all these results. Right. So then for I in Steam, so this is if you want, this is a loop over variables or features. Just let me print this, because when we execute this, we will probably, this will be telling us where in the algorithm or where in the tree we are doing. So checking splits in variable. Let me put this like this. So there will be x1, x0, or x1. Sorry. And so here, I will just use first of all the case where the type of variable is continuous, because I'm saying that the two variables, so this will be in a list where for arguments, for example, C, comma C, because it's continuous and continuous, because both variables are going to be continuous. So if the two variables are continuous, then I need to define actually the cut values. So I have I need to define my grid, right? So where I split these inputs or each dimension. And this is defined here in cut values. So cut values. Wait a second. Yeah. So here, the thing is that I am printing what I am trying to check. So let me go to this. This is written here, but I was trying to write it this line. So this is my cheat sheet, if you want. Here, so cut values is this cut vals. Sorry. So it's a linear space between the minimum of the variable and the maximum of the variable in question, given some number of cuts here. Okay. Number of cuts is going to be like a global variable. Okay, so once I have the cut values here, then I do the following for this value in. So this is a variable that will cover all the cut values. Okay, that I have just defined. Then I am evaluating. So I am first of all splitting the data according to the function just created before. Right, so this is the data and then the index of the variable and the value. So this is exactly what I'm doing here. So, and once I have my left and my right, then I need to create two genies, the genie for the left and the genie for the right. And this genie for the left and for the right is going to be genie of left and 0, 1, because those are the classes. And similarly, the one from the right. Okay. So once I have the genies for the left and for the right, I need to combine this left and right in the following way. So I need to. This is something that we didn't say on Friday, but this is the usual practice here is to define some like weight for the left or for the right, and this is just a weight reflecting the fact that the left and the right may not have the same dimension, may not have the same number of points. Sorry. So I need to correct somehow for that, and then this is just left. So this is a fraction of points that went to the left, and the fraction of points that went to the right. And finally, the Gini value of the split is a combination. So it is a Gini left weighted by this P left plus Gini right weighted by P right. Okay. So this is the way this is the final value of this is the figure of merit of the split, if you want. And I do this for all the values defined here. Okay. And then I am just appending the result of the Gini.
In
Yes.
the split, the weight of the Gini right is multiplying the weight left.
It's not correct.
Yes.
Thanks a lot. Yeah. Thanks. So then I am appending this result. So, but I am appending the index of the variable, the value that I am using right now, and the G split. Okay. Okay. So once I have done this, then I need to evaluate what is the best split. The best split is the following. So split res. So I have in split res, this is the an array of all the possible splits of the two variables in this case. And actually what I'm doing now is the following. So this is going to be so let me put this one line below for you to understand what I'm doing. So if I have the array, because for now that was a list, I convert this to an array, so no problem for that. Converting this to an array, I'm getting only the third row. Remember, in Python you start with 0, so it's 0, 1, 2. So this is the third row. The third row is just this value. So this contains, for all the possible splits, the Gini split res. Okay, for sure. Because I am outside the function. But what I'm saying here is that this is only taking into account the Gini. So I am, by doing this, and then I have all the Ginis, and then what I need to do is to take what is the index that minimizes this. So in other words, the argmin of that. I take the argmin of this. Okay. So this is what I am actually putting inside my function here. Let me see if I got it right. This, yeah, it should be right. Should be correct. So in other words, from all the possible splittings, I am evaluating the one that has a minimum Gini value in this way. And then now let me return this. So print what I wanted to print in this function, and what I wanted to print is a dictionary. So I don't know if you're familiarized with Python dictionaries, but it is very easy. So the output of this function best split is a dictionary where the component var is the first component of best. So remember that this is this best is like a 3-component vector where you have the index of the best variable, the best value, and its corresponding Gini. So var is going to be the index of the best variable, which is stored in the first component. Then, as a second element in our dictionary, we'll have our value here. And then again, the way I printed this is not good. So, and then let me just take this part. And so another element of my dictionary that I need to take the output to define is this left. And left is nothing but the data that went to the left here, right? So I'm just splitting that data, and so the first component of the function is split, and the other component of the split function. Okay, I will put a comma here for better. So you see that I am storing, so the best split, the output of this split is a dictionary where I store here in var what is a variable, the best variable with the best value, and the data that went to the left and the data that went to the right. And this should be okay, I hope. Let us evaluate this. PhD for in French. PhD, let me see.
It's lagging an in.
Ah, thanks. Okay. So let me see if this works. Best split data set. And in X types, I will write continuous and continuous because those are continuous variables. Encodes, it's not defined. Yes. So let me write encodes. I think I put it equal to 40 because I need to define what is my binning or in how many intervals I got my my access. So I am checking the splits, and then left is just an array of points, and right is just another array of points. So the thing is that with the dictionary, so let me put this. If I store it here, then I can say, okay, best split, and this is the way. This is why dictionaries are convenient. Left is going to give me best. Sorry, split. No, it doesn't like it. Best split. This is only giving me the left part. If I take the right, it's going to be analogous, the right part. Or if I am just plotting, I'm just interested in the variable. It's telling me, okay, the best split here was in the second variable, so the y-axis. Okay, so that's why dictionaries are quite convenient, and it is quite used in the machine learning.
Sorry, Brian.
Yeah.
Can you go a little bit to the split function?
Yeah.
Okay. Thank you. Thank you.
Anyway, so we have now a function that tells me, okay, given a data set, I am evaluating what is the best split. Okay. It's probably convenient. Let us put actually encodes here. It will be more convenient than this. So I'm just putting 40. This is the number of cuts. Right. Okay, let's go on then. Then now what we need to have, another element that we need to define is what is happening if we arrive at a terminal lead. Remember what we were saying on Friday in decision tree, there are many criteria for deciding where to finish, where to cut. So one of them is something that we are using here is the maximum depth of the tree, which means how many nodes, how many levels of nodes you will have. This is one condition. Another condition may be, for example, if there is a minimum number of elements or points in a given left or right region, let's say. And there are other criteria, no? But so what? Once I decide that this is that this is a terminal of my tree, that this is a terminal leaf of my tree, I need to print. So what is the result of that terminal? And the result of that terminal, we'll store it in this. We'll compute it in this function called val terminal. This will take some data set. And I'm just doing here the following. So first of all, I am extracting all the outputs. Okay. That as before. So this contains all the outputs of my data set. And then I'm just computing the argmax of that. So this is just numpy argmax of but you remember that here, imagine that I am in some patch of my data set. So you will have many points with 0 and other points with 1, because this is the 0 and 1 classes. And I'm just interested in the one in the class having the largest amount of points. So this I am doing it with this line. So first of all, I'm calling numpy unique. Numpy unique is giving me the unique elements from an array which may have the elements repeated. For example, if I have an array of zeros and one, by calling it numpy unique, I'm just output. I mean, the output is just 0 and 1. Okay, so numpy unique of the y set, but return counts true, saying that unique will give me not only the unique values of the array, but also how many of them you have in your array. So, for example, let me just if you're not if this is not too clear, for example, if I put numpy unique of so let me see if this works. Okay, I will put an array, numpy array of 0, 0, 1, 0, sorry, 0, 1, 0. If I do this, wait, what did I do? No, function object is not.
You put brackets instead of
What did
for
I do?
the NP unique.
Yeah, sorry. So if I do this, I obtain only the 2 elements. But if I put return counts true, it is giving me, say, okay, from this first element 0, I have 4 elements, and from the other value, I have 2 elements. So by having by taking only the second output, I'm just outputting, having this output. I here have only the counts of each of the elements, and by computing the argmax here, if I compute the argmax of this, it will give me, of course, 0. The argmax of this, it will give me 0 because 0 is the value. So the position of the value that is more frequent in this data set. All right, so then here, this is what it is storing, what is that position. And then I am just returning, oops. So what was this? Argmax. And then I'm just returning for all the data set, return counts true. So I am returning instead now the 0 and argmax, right? So I'm just returning here what is the variable that the index of the variable that corresponding to this argmax here. Okay, fine. So let us continue if everything is clear so far. It's clear. Okay. Okay, so here now, if this is clear, what everything is doing, then the following is going to be probably the most important function in this in decision tree, which is called the growth function. So this is a function. This is a recursive function that I will explain things before. That is going to be the responsible for growing the tree. If you want. So first of all, let me just put some lines here for explanation. So node. So what I'm calling node here is going to be just the output of best split. So in general, node is going to be a dictionary having elements of variable, value, left and right data set.
Excuse me. Could you
Yes.
test out that function, because I've written it as it is and it's not running for me.
This one.
Yes, Walter.
This one. Okay, let us put here an array and an array of 1 0 1 0 0 0. Okay, too many indices for an array. What is that? Okay. I said. Yeah, because the array is not in the shape.
Okay. Yeah.
So you see,
Okay.
I am expecting. So this guy is expecting a bidimensional array, and I am testing the function.
I also tried out with a one-dimensional one. Yeah.
Yeah,
okay.
but if you try with 2 dimensions, it's going to work. Yeah. So first of all, the explanations I was making. Node. I am defining node below as the output of the best split. Another. So it contains these elements, right? So node var, node var, node value, node left, and node right. Okay. Okay. So then grow is going to have the following. So node has an argument max depth, and this is one of the hyperparameters of my decision tree. I just want to cut my decision tree, for example, in the with 4 levels, if you want. Depth equal 4, if you want. Mean size, which is the minimum size of elements, number of elements I want to have in a leaf or in a patch, and depth. Now you will understand slowly what is going to happen. So first of all, left and right, I'm taking node left and node right. Okay, so do you understand what this is doing? And once I have defined what is left and right, let me delete the node because I will redefine it later. So I am deleting node left, and I do the same for node right because I just have it there, and I will redefine it below. This is going to be a recursive function in the sense that it is calling it to itself in order to build the tree. Okay, so once I have left and right defined, then I first of all let me check for empty left or right, which lead into a terminal. Right. So the way to do that is just very simple. So if length of of left is 0 or length of right is 0, then do something. Or let me just print it this, because if this happens, I wanted to know it. Empty left or right. And then I'm actually doing what I need to do, so which is I am saying that the node left, and now I am redefining this variable. Remember that I deleted here the variable, but now I am creating it again. And now instead of a node left, instead of being a number of points going to the left, it is going to be a val terminal of left. But I am doing it the same for, since I am doing the same for either for 0 left or 0 right, or empty left and empty right, I am doing the same for right. And then let me just put here left plus right. So what I'm saying here is that no matter whether it is the left or the right, which is 0, I will assume this is a terminal lead, and then node is going to be either left or right, is going to be just the terminal value here. And don't be confused by this left plus right, because remember that either left or right is 0. So if right was 0, then this is only val terminal of left. And then I am just storing this in the nodes, left and right. And similarly, if left was 0, okay? And then just, let me just, sorry, return if that was the case. Now, okay, I have checked for empty left or right, and now I need to check for max depth. Also leading to a terminal. And this is simple, because if depth is larger or equal than max depth, which is saying if when I call this function from itself, so I will down here I will call the function from inside, but by increasing the depth plus 1. Every time I'm calling it, I increase the depth of 1. But if this depth is larger or equal than max depth, I need to stop. And I need to stop, and then I'm just notifying this. Let me just notify this by max depth reached. And if this is the case, node left and node right is going to be val terminal left and val terminal right. Okay. So each of the two portions at the left or the right will have the value corresponding to the majority class given by this val terminal. Okay, so then let me print it. I will print values of left, so values. So the one from the left is going to be this node left, and the one from the right is going to be the node from the right.
Sorry, Brian, can I ask you something?
Yeah.
So when you have an empty left or right, so you are putting left and right in the node as val terminal, left plus right. Could you explain again why?
if either left or right is 0, then either this term or this term is 0. No.
Okay.
So then I am saying that imagine that right is 0. If right is 0, then I am saying that node right is equal to value. That node left is equal to val terminal left. So all the points in that split went to the left, and then I'm just taking the value of the majority votes there, and by doing this, node right. So your question is why node right is val terminal left?
Yes.
Let me think. Why node val is? So it is like to say that if a test point after I did all this went there, I am assigning it as since it was empty from the training points. I am assuming that it is also the class defined by the majority vote of the left. So imagine do you have a situation where a test point went down on the tree, and by going down on the tree, you end up in a patch, in a region where you have no training points.
Okay.
A priori, you would say, okay, I don't know what to do now because there is no training points here for me to evaluate. So what this assumption is doing is saying, okay, I will just assigning it to the one of the right because this is the closest I have.
Okay.
Or something like that.
Okay, thanks.
Yeah, but it is a good question because indeed it is ambiguous what your decision is if you end up in a region without training points. It is ambiguous. You can decide this or you can decide otherwise. But you need to make a decision. Yes. Yeah, very good point. Thanks. Okay, so let us finish the grow because it's already 4:12. Let us finish in 5 minutes this function, and then we make a break. So first of all, before growing the tree, I am trying to evaluate whether I am actually in a terminal leaf or not. So either because one of the regions are empty, or because I have reached the maximum depth, or so let me see. Okay, so now let us grow the tree, but without with a condition first. So grow left branch. So I will do this unless there is the minimum size. So if length of the left is smaller or equal than mean size, what I do here is to again terminate so not growing anything, but just say that this is just val terminal left. Okay, and let me just inform this. In my when I run this, it should inform about everything. Mean size found in left branch. Okay, so left value equal node left. I think like this. So either I have this, or I do grow my tree. Let me just inform this by saying growing left branch. And growing left branch is the following: is saying that node left, instead of being a val terminal, is going to be best split. So the output of best split in left, and of course X types. X types is again a global thing that I should define at some point. So that on the one hand, and once I have the node left, I call the function from inside. So I call the function that I'm actually building. So this is why there is like a recursive call here of node left max depth, the one mean size, and this is important. Now I increase the depth by 1. This is what I was saying before. Okay. Then I will do exactly the same for the right branch, and then I am explaining, and then we just take the break. Grow right branch. So by growing the right branch, let me just like copy paste this because it is very similar. Oops, what? I'm just copy paste this. So I am making sure that my right is not smaller or equal than the mean size. If this were the case, I'm just saying that node right is a terminal. I inform it. And just replacing left by right everywhere. Growing right branch. And then saying here that right is best split of right, and grow it from the right. Okay, so that's it. And the function finished here. So note that by writing this in this way, know that the tree will always tend to grow always left as far as it can go, because the first thing I'm writing here is like I'm trying to grow first the left branch. But since imagine that now I am in this situation, so I am not yet in this condition. So I am arriving at this situation, I grow a left branch, and then I call again the function with a level of depth increased, and then I call again grow, etc. So note that by writing in this way, this is tending to go to the left all the time, to the left so far, I mean, as far as it can go. And when it cannot go to the right, to the left, sorry, it's going to go to the right. And this is, I mean, you will see it when we test, when we execute this, you see how this is working like that. Okay, so let us, I don't know if evaluating this, let us wait for later to evaluate this function, because I am evaluating it inside another function just to test it. Okay, so let us take a break if you agree, and let's come back at 15 past, if you don't mind.
Brian,
Yes.
during the break, could you please show in the screen the best split function, because I think I have a typo somewhere, so during the break I can check it.
Yeah.
Thank you.
Or you can take a snapshot or a screenshot.
Okay, that would be nice. Thank you.
Yeah.
Also in the grow function,
Yeah.
we put X types, but we aren't introducing X types as an argument of grow.
So far, I haven't introduced the X type as an argument of grow, but probably we should. But
yeah, just because best split uses it, so I.
because I have changed. No, 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 no,
Yes.
no.
Okay.
No, yes. So here, best split. Yeah, you see, X type. I'm calling it here and here. So if I just define X, yeah.
What I mean is that then you to call grow you have to give X types to grow, right?
Or
because we haven't defined. Yeah, or outside.
Or outside in a global,
Yeah.
definition.
Okay.
Yeah. I can do it here, for example. Yeah, let us do it later. So yeah. During this break, if there is any other question, then we can sort it out.
Brian, I have a question.
Yeah.
So we've defined best splits with 3 arguments because we included end cuts. So should we modify
you are
those
absolutely
also?
right. You're absolutely right. Yes. End cuts. Yeah. Thanks. This is I would make an error here. So let me see. Sorry. 3 arguments. The last one is end cuts. Yeah. Absolutely.
Thank you.
Thanks to you. Okay, so let's continue if you are all ready, or almost all ready. So as I was saying, let me continue with writing the two more functions or 3 more functions I need, and then let's like check the functions all together. So the other thing I need to do finally is to build the tree. And this is going to be a very short function using the grow function, which is the best one, the main one. So the argument of that is a train data, max depth, mean size. Yeah. And I am calling root to be the first node, if you want. The root of the tree is like the first split that you make. So if I go best split of my training data and the X types, here, Right. So, and then let me just say what was this. So root node. Wait. Do you hear me?
Yes.
Yes.
Okay.
So,
So
sorry,
no,
but-
it is because I was muting everyone, but then I muted myself, so I needed to unmute myself. Anyway, so so I'm just informing what I'm doing here. A root node, the variable and the value is given by root. Since this was a dictionary, you remember, var and root value. So here, what I do now is going grow, and now I use the function that I wrote below and above, sorry, with max depth and mean size, and which value of depth 1, because I am at the root, right? And then return root. So let's try to evaluate build tree. That if this work, then I will evaluate. It would mean that grow function we wrote it correctly. Let's say. So let me just try build tree data set. I'm just before splitting. I am just taking the whole data set to be my training. Max depth. Let me put it 4. Mean size. Let me put it 1. I think. Yeah. So let me see what this is doing. It's doing something that is not good. Yeah. Okay. So X type. Forgot to. So X types here is just CC. And then again, doesn't like it, end cuts. End cuts. So if end cuts here, because I am changing a bit what I did.
It's on best split. You have to add it at the end.
No, it's not here. It's up here.
Yeah.
Thanks. End cuts. Okay. End cuts equal 40. And what is now? Best split. I didn't execute it. Yeah. So thanks. So this is the result of growing the tree with all the data set as training. Just so you see what is happening here. And I'm sorry, at this point I realize I didn't come up with a graphical solution, so this is very shabby probably. But what I'm able to do here is to follow what is happening. So I'm just at the root. I'm checking the splits, what is happening in the code, checking the splits in the first variable and the second variable. From all of them, I get the best split. And it turned out to be the second variable, so variable 1, with this value. So I know that the root split is in the y-axis of my data set around this value here. Then growing left branch. And then by growing left branch, of course, I need to check 2 variables. So then I grow left branch again. The other 2 variables, and the mean size, up to the mean size is found on the, so let me just, y branch. So something, I forgot to print something at depth 1 in grow. Let me just do it. I think I forgot to print something in the in the grow function. Yeah. So let us add here the following. So while growing the left branch, if I am not in the minimum size case, so in the else, I forgot to write this. So this is depth equal depth, and then here variable x plus string of the node. Okay, let me put it here because if I probably get grow, I'm just taking it from here, and then you can copy it if you want. Okay, this thing. So I am when growing the branches, I am like showing the depth, the variable, and the value, and then I do exactly the same, and then I grow, and then I do exactly the same here before growing the right, but right, replace it by, so left replace it by right, sorry. Yeah, now let me just check this again. Okay, so what I was saying, the root node was in the first in the second variable. Then I grow a left branch, and after checking the splits, I am at depth 1. So this is the first level of the tree, and this node turned out to be the split at this depth turned out to be the first variable x0 with this value here. And then as you remember, so the way this function is written, it is like it is trying to go left as far as possible. So it's growing left again, and then it reaches depth 2. Again, the best variable was the first one, x0, with another value of the split now. And once I have reached depth 2, then it turned out that I reached the minimum size in this left branch, and the value turned out to be 0. Now I am at depth at this depth 3, growing, sorry, right branch at depth 3, because I couldn't go more to the left, so I go to the right. So depth 3 here is variable 0, and then of course once I go later than depth 3, I already reached depth 4, which is the maximum one, and I need to stop there. That leap, if you want. Then I'm going right again here, and after checking the splits at left depth 2, so I am now at the higher level in my tree. So I get this, then I go right, etc. By doing all this, you can follow what is what was actually the history of the tree, let's say. And so forget about this output. I will later explain why I am printing this. Okay, so let us now after I have built the tree, I need to make a prediction. Predict, and the arguments of this is row and node. So if row, sorry, if so row is a point is a point in the parameters in my data set. So now by doing this, I'm saying that if the variable here of that node evaluated in this data point, if this is smaller than the required value, then I'm doing something now I will explain. Is I'm using a function which is called isInstance node. And this is to say, if a node is actually a dictionary and not a terminal, because if it is a terminal, it is not a, it is only having one value, one scalar value. But if it has child nodes, it is going to be again a dictionary with child data sets, etc. Then return predict, and this is recursive again. I'm calling it from itself. So
Sorry.
node, yes.
What is row? Is a function?
Row is one point in your data set, in your test data set, consisting of a value of a first variable, value of second variable, etc. Right? But my data set has this shape. So this is one row.
Okay, and when you call row in the if command, how are you doing?
Yeah, so here row evaluated in a node var, for example, imagine that the variable of that node is the second variable. So that will give me, if this is the row, that would give me this one.
Okay.
This value. And if this value is smaller than this value here, specified by node, then I go left if you want. So I try to see what is the node left. If this is a dictionary, then I call the function from inside. But now by calling the function again from inside with this argument, I am now going down a level in the tree. And why is that? Because remember, this is why I printed this. So imagine that to this predict function, I give all of this. Imagine that I give all of this huge dictionary, sorry. Right, and by going down in a tree, so if now I take what is the left component of this dictionary, I go here. And if I go left again, I go here, etc. So you see that by calling it in this way, I am getting forward in the depth of the tree. So then I do this, if instance return that, else return predict node left row, and node left, sorry. Node left, exactly. And else I do the same for the right. If the right has child, it means it is a dictionary because it contains more stuff, not only one number. Then I do analogously here for the right row, and else I just return the right. And this is how I will a prediction. So I will for a point in my prediction, meaning, for example, imagine that this is my test data. For a point in my prediction, I will evaluate each point here in going down in the tree to through the left and through the right.
Sorry, Brian,
Yes.
can you go to the build tree function? Okay, thank you.
Okay, so okay, I have then two more very short functions. Decision tree now is going to have train, test. Now the train and test data, max depth, mean size. Please mute yourself, please.
Sorry.
Yeah. Like this, then 3 equal to build 3. I'm just calling the function, this build 3 function there, train max depth, mean size. Let me just print something here just for clarity. Then I'm printing the 3. So 3 equal, let me just put a new line here, 3. Okay, then predictions on this test data, I will store them in this array I'm trying to fill. So for row in test, which means for every point in my test data, then I will store in predictions the result of predict. And predict has 3 and row. And return predictions. This, and finally, and I won't bother you anymore about this, I need to score. So the score is how well my prediction was on the test data. So I am taking the observations, which means the observed outputs, and the predictions. And this is easy. This is just the fraction of correct points. So for I in range, the size of the observations, let's say the size of my test data. So if ops in I is equal to pred in I, then correct increase it by 1. Otherwise, you do nothing. And then you just return correct divided by the total length. Okay, and that's it. So what I'm doing now is to test the whole thing, but I'm now checking this by splitting. So the main routine now. So data set I have already defined it. So what I do now is to split data set in training and test. And in order to do that, okay, let me just, for reproducibility, let me use a random seed. And I will do some permutations, some random permutations of my data. Length of the data set. And I will shuffle my data set randomly with these permutations. Okay. Once I have shuffled this, then I define what is the size of my data set. Let's take it to be a 20% of the total length of the data set. So test data is just equal to data set from 0, from the first one, to test size, so the first 20%, and the training data is going to be the rest. from test size to the n. Okay, something happened here. Model number one has no permutation because it's permutation, not permutations. Yeah, sorry. All right, so now if you're all with me here, I'm just doing the same, but now I am calling decision tree instead. And decision tree instead, I am not only training providing the training data, but also saying what is the test data with the 4 of maximum depth and 1 of minimum size. And by doing that, I obtain this. I mean, similar thing as before. And the resulting tree was this one. So there is an error here. Val, what is that? Sorry. It's value in predict. Sorry, in predict is value, not val. Yeah. Okay.
Sorry, could you show me 1 second the function build tree? No, not build tree, best split. Sorry, because I think
split.
Yeah, I think I missed the part when you add the NCAT.
This one.
Yeah. 1 second, I'm going to take a picture.
Hello. This might be a little bit late, but if somebody has any doubt with the codes, the session is streaming YouTube, so you can go to the stream and just rewind 10 seconds or go to the part on the stream.
Yeah, this is also true.
It's easier for you to get the code.
Yeah. Okay.
Thank you.
So now you say, okay, I predicted something, right? So for example, predicted, let me print what this predicted has. So it has a series of ones and zeros. And then if I go to test data, if I go to test data, well, the labels, it is this. So I am confronting my predictions with my test data. And then let me see how well I did. So model score, because I defined what the score was. Model score is a score that the function we defined, above, with observations and predictions. And let me print, what is this? Model score. Now it's 80%. I don't know why I had the more when I did it. Okay, let me see. Left random seed. Yeah, I don't know. 80%. Let's say. I got 95 actually, but by doing this, but I got 80. And it may be due to some like random initialization here.
Ryan, probably when you reshuffle your data more than once, you have different reshuffles. So if you rerun all your notebook, probably you're going to get 95 because I did.
Okay, let me try. Thanks. So restart and run all. Yeah, let's see. Yeah. So why was that?
Because when you reshuffle, when you invoke NumPy random function, each time it updates the seed so as to ensure randomness. So
Yes.
if you permute more than once, you obtain different permutations.
Yeah. Right. Yes. Yeah, you're right. Yeah, thanks. So okay, I got this. Okay, this is 95. This is what I was getting in my when I was writing this. And let us now. So of course here what I'm doing need to be this needs to be improved in the following way, and this is something that probably is a good idea for you to do. So one thing that you could do as a homework for those of you who need homework is to implement cross-validation on this. Let's say 5, k equals 5 cross-validation on this. In the sense that now of course the score is going to be different for each of these folds, and then you need to average. Okay, so this is something that you should do as a homework. But let us compare the result of these 3 we have built from scratch, going through all these long steps. Let us compare this with the output of the built-in function from sklearn. Okay. So let us import now. Let me just say here. So compare with scikit-learn models. So now, in order to do that, let us do the following from sklearn. Learn. Okay. .3 import. First of all, we compare with the decision tree. Decision tree classifier. And I am also importing something, some nice tool that they have in order to print it, which is plot3. Okay, so let me see if this works. Okay, that works. And now I am saying, okay, imagine my classifier is this decision tree that I just imported, this library, where I have many criteria here. So you will see all the criteria in a moment, but I need to first specify that I want to optimize this by using the Gini and not other thing. And I'm also trying to be in a similar condition to what we just did, which is taking maximum depth equal to 4, right? So I have done this. So I have loaded my classifier. Then another thing that is useful when you use this sklearn is that it implements for you automatically the cross-validation, like here. And then, as in every model that you invoke or that you want to use from sklearn, you need to fit the model, which means the training part is happening here. So you put classifier dot fit, and this is a fit is a common method to all the models of sklearn. And then I am saying train data. I should have called this X and Y. So let me just to avoid confusion here, let me put X train equal to train data. Sorry, all the points and all the points except the final column, and Y train is this, just the final column. And then I am calling here, in order to fit it, X train and Y train. I think this may work. Let's see. Okay, so when I do this, I already fitted the decision tree, and then actually sklearn is printing me by default the information of the parameter that I have assumed. And there are many parameters that I don't want to enter into the details of that, because you can study this in the literature of sklearn. But I mean, this is what we have defined it, MaxDef and the Gini. There are other choices that you can, if you go to sklearn decision tree, then you see you can specify here many things if it opens. I don't know. Okay, so you see many criteria here, and each of them has its own explanation, but I don't want to enter into the details now on that. So what I want to do is to compare exactly what I have. So classifier that I just trained dot score, and this is the one, the thing that I am comparing with my 95%. So then I say, okay, so let me do the same for the test. So this is test, and this is test. I define also Y test, like here, and then I am just X test, Y test. Okay, so by doing this, I need to get something similar to what I got. If I implemented the above thing correctly, I need to do something similar, and then what I get is 90%. So finally, this simple thing that we did from scratch gave a little bit better than the default performance of my of the sklearn decision tree. Okay, now let me use this functionality, which is very illustrative. Plot tree classifier. No, sorry, plot show. Yeah, so it's hard to read, but here what you're having is the value of the value. I mean, for example, for the root node, you have x1, if you can read it, and this is the value of the best split at the root with the corresponding Gini, number of samples, etc., and the value on the left and on the right. And then somehow this nice tool gives you the like the tree that was built. And not only that, but it's also possible to plot the decision boundaries. In order to plot the decision boundaries, let me do one thing because there is only 10 minutes left. Let me just copy paste this and I explain. The only thing I'm doing here is to making a grid with mesh grid of points from the both dimensions. I'm doing a mesh grid here with this step, and I am just using the prediction of the classifier on each of these points. Okay, and when I do this, I obtain the following, which is just is telling you or is showing you how was this classified. Sorry, or the splits that that were used for the classification. So, for example, the best split at the root was in the x1 and was 0.02. So this is probably this one here. What we should be? Yeah, I don't know why this line didn't go to the other extreme, but I mean this should be the correct. I mean this should correspond to this one. It's somehow that I don't see it now, but it should correspond to these splits. Okay. So, is there any question so far? Okay, if not, in the last 10 minutes, since the use of sklearn is quite out of the box, let me do one last thing for you in this hands-on, and it's the following: is trying to compare this performance, 90% or 95%, with the one that you would get from a simpler classifier, which is logistic regression, which we also commented on Friday. And that you remember that the logistic regression is a linear model, which means that there is only going to be one line as a decision boundary, one hyperplane as a decision boundary from the two classes. And naively, what you would expect by looking at this data is that logistic regression is performing worse than decision tree, simply because you see that this data is not linearly separable, at least not in this plane. Another story is that you take that plane, you transform it into some transformation. So with this phi plane that we are talking about in the lectures, and then there you may have a linearly separable points, but this is not the case right now. So what I'm doing is to try to evaluate the performance of logistic regression on this data set. So I'm doing this with the sklearn, but in the second hands-on session of neural network, we are like, as I was telling you, logistic regression can be thought of as quite a simplification of a neural network, in the sense of it's a neural network without hidden layer. So we will build, if you want, the algorithm from scratch of a logistic regression and for a neural network. So what I'm trying to say here is that I will put logistic regression out of the box with the sklearn, but in the next hands-on session, we will build it from scratch. But let us, for the moment, use it. So let me put here logistic. So check performance of logistic regression classifier. So when I do this, let me right click. So the workflow is the same every time. So I need to import this. Sorry. So how is this imported? So from sklearn.linear model import logistic regression. I think this is correct. And now I'm using this. So classifier is just logistic regression. And then let me define two things here. The solver, you remember that logistic regression was a method whose optimum parameters needed to be solved numerically, not analytical, because it is not an analytical model. So the numerical optimizer, if you want, is called, there are many possibilities. One of them is LBFGS. It's just an optimizer, just an algorithm to find a minimum of a function. And let me just go to penalty none, and penalty here has to do with the fact of using a modified or a regularized cost function, which I don't want to do that. I don't want to do now, not on this topic. So let me evaluate this. Okay, and now I fit it. The same way I fitted the decision tree, I fit logistic regression. Sorry. Train, Y train. Okay. There are some parameters here. I don't want to enter into details on that, but some of these parameters you need to tune. And let me just see the score of the model that I just fitted. So I just trained the model here, and now I see the score in the test data. Sorry, it's test. Okay, 85%, which is what we expected. So we expected to have a lower performance, and this is just because the decision boundary is linear, and it is not quite linearly separable. Okay, so the last thing I'm doing, I am not writing it because it may make it waste time on that. But let me just let me see if I can copy this just to plot. Okay, and I copy this. Yeah. So this is the result of the decision tree, and let me explain that. So this is the training, actually not the training data, but the whole data that I'm plotting here. No. This is actually only training data. Yes, this is only training data. And in color is the probability assigned to which class? To the second class. So I am computing here with this method. This is a scalar method, predict proba. This is predict the probability. So you remember that logistic regression is a probabilistic model that the output of which is the probability of a given class given an input. So I am collecting here the probability of the second class given an input, given all the inputs. So the probability of yellow class in this case. So as I move towards the bottom right of the plot, the color is darker and darker. It means that the probability of being class 2 or class yellow is higher and higher. And as I move towards the opposite side, towards the top left, the probability of being class yellow is smaller and smaller because the probability of class purple is larger and larger. So somehow the boundary of equal probabilities is somehow here in between. The decision boundary corresponding to probability equal 0.5 is something somewhere here. But of course, you see that this is, so you see it now. So this is a linear decision boundary, and which is misclassifying. For example, these points, these yellow points are surely misclassified. And in the same way, these purple points will surely be misclassified because this is obviously non-linear, right? Okay, so this is that's it. I don't want to include more material today. So is there any question? In general? Am I online or I am talking alone?
No. Yeah, you're
Okay. Sorry. Because I mean, sometimes I'm staring at the screen and I don't know whether I was disconnected or something. So
yeah, I mean, will you upload these files also?
Sure.
Okay, because
for sure. I will upload it today. Yes.
Okay, perfect.
Yeah. Okay, so I hope this was useful. At least, I mean, at least this part, because it is only when I did this myself that I actually could say, okay, I now understand what the decision tree is doing. Because before, I mean, for me, the disadvantage of taking the model like this with from sklearn, etc., is that you actually don't know what is in the guts of that. So I just wanted to make this once in my life in order to see that I understand what it's doing, and later on I can use this library. But I already know, I am confident that I know what it's doing, or how the decision tree is working. So that's why, of course, you don't need to implement this from scratch for every problem you had. But I don't know. Probably this is me, that I am old school or something. Okay.
Sorry, Ryan, can I ask something that has nothing to do with this lecture? Last lecture, you gave us an assignment with the Bayesian classifier notebook, but I cannot find it on the Indico webpage. Could you please upload it?
Yeah, I will upload. Yeah, I forgot. Sorry. Yeah. I will upload this right away. Yeah.
Thank you very much.
Yeah.
Thanks.
Okay, so if no more questions, let's stop here and then continue tomorrow with the lecture on neural networks, I think.
Okay, see you. Thank you.
See you. Bye-bye.
Bye-bye.
Thank you. Bye.
Pretty
Bye.
interesting session.
Thanks. Bye. Okay, stop.